وي سي زرير تبارك الله عليك. صافي راه مونسيا في الفيسبوك بدي ندير لا بريزونطاسيون باش نقول لك. سي الحسين الورقي.
نعم نعم
داكور سي بون صافي.
جوست لا كاميرا.
Yes, we are waiting the manager from the university to share the conference now. Okay, Professor Warri, can you introduce Professor now? The conference of Professor TADEUSZ is shared on YouTube and Facebook.
Thanks, Professor Hamouti. First of all, thanks and congratulations for the organizing committee, Professor Hamouti, Professor Jeffali, Professor Innawi, for this brilliant conference, and it's really great and so well organized. Dear colleagues, dear participants, dear audience, welcome to this 11th webinar keynote of the 4th International Conference of Materials and Environmental Science, New Materials for Sustainable Energy Development. Our speaker this afternoon is from the University of Technology and Humanities of Random, Poland. His conference is about the very interesting topic of spectroscopy and magnetism used in environmental control. Professor TADEUSZ SZUMIATA has his expertise in the applications of Mössbauer spectrometry in environmental sciences, His great passion is joining these techniques with advanced magnetic methods. His focus is based on the iron speciation in technogenic magnetic particles, which are natural carriers for heavy metals in soils, airborne, particularly geothermal water sediments. He was awarded his PhD in 2002 from the Institute of Physics of Polish Academy of Sciences in Warsaw. He is an associate professor at University of Technology and Humanities in Radom, Poland. He participated in scientific internships in Finland, France, and Great Britain. Besides environmental studies, he is an expert of magnetoelastic effects, magnetic nanomaterials, magnetic defectoscopy, and modern mass metrology. He has close scientific connection with Mohammed I University of Oujda. He published more than 56 papers, cited by 238 documents. His H index is 9 on Scopus. The speech of Professor SZUMIATA is entitled Mössbauer Spectra Analysis and Magnetic Hystereses Decomposition of Iron-bearing Environmental Samples. Professor SZUMIATA, thank you for being with us today. You have about 35 minutes for your speech and wish you good luck.
Good afternoon. Bonjour. I would like to thank you, Mr. Professor, for this very nice introduction. I also would like to thank my friends from the university, Mohammed Premier Oujda, for giving me an opportunity to be a key speaker during this prestigious conference. Encore grand remercie pour votre grande hospitalité pendant ICMES conference l'année dernière. Okay, I would like just to go directly to the objectives. And what are the objectives of our research? We would like to use Mössbauer spectrometry analysis for differentiation of iron-bearing compounds in many kinds of environmental samples, like soils, also fly ashes, and ventilation dusts. We would like also to find the mineralogical characteristics of technogenic magnetic particles, which are emitted by various pollution sources, various emitters. I would like also to answer the question if such mineralogical characteristic of technogenic magnetic particles is enough good to be an indicator for the specific emission sources, to be a good identifier for such sources. I also would like to say a few words about new simple procedure of magnetic hysteresis loops decomposition and their applications in the case of multi-phase environmental samples. And also very interesting question for me is the presence of metallic iron in different kinds of environmental samples, especially in ventilation dusts and also in fly ashes. The first group of the samples, one moment, are the topsoils, which has been collected from fields, from the forests, which are located near some metallurgical industry. And they were collected using special soil sampler by my colleagues. 3 locations of sampling was in Poland and in Czech Republic, just at the border. And all these 3 locations are just fields and forests near ironworks or steelworks, which are operating now and was operating and has been operating for many years. The 4th location is in the north of Norway. It is Mo i Rana, and here a very special iron ore dressing plant is located. Additionally, we considered 2 other samples. We call them reference samples, and they are more natural or completely natural. In the case of the first of them, collected in Bjørnvatn, it is really to the north, very north of Norway. It is not displayed here, just at the border with Russia. There is open cast iron ore mine. Yes, and it is the first reference sample, and the second one, just from the south of Norway. These samples are just subsoils, natural soils taken from the background, and they are very rich in natural lithogenic magnetite. And you can see here 4 Mössbauer spectra taken at room temperature for the samples, not crude samples, but specially prepared magnetic separates, because we are interested not in the soils themselves, but in the technogenic magnetic particles which are settled on the ground. And we also made Mössbauer measurements for these 2 reference natural samples. And what we can see from this spectra, what we can find in the samples, we can see hematite, we can see components from magnetite, small amount of goethite, and still quite huge amounts of aluminosilicates, which are of natural origin, of soil background origin, but not of our interest. And what is really interesting here, that when we come back maybe to this spectra, it was impossible to fit this spectra, this part concerning the magnetite, using as typical with two components describing A and B sides of iron, tetrahedral and octahedral one. It was not enough. It was necessary to introduce some additional, more broad lines, and we interpreted them as a contribution from the surface of very defected grains of magnetite, or maybe it is some new phase related to the magnetite, but very defected magnetite. It is something new, not visible previously. And I present here some graph when you can see the contribution of these additional components, let's say surface component. And in the case of the sample taken from the Czech Republic, this contribution is over 40% related to whole amount of magnetite. So this magnetite was very defected, we can say. And in opposite end, we can see this sample from Mo i Rana, this Norwegian sample, more natural, just from dressing plant of the iron ore. And here this contribution is relatively small, about 10%. And in the case of these strictly natural samples, 2 reference samples, there is no such contribution. The presence of this contribution could be somehow related to the size of the grains. Here you can see just optical micrographs of the samples with the huge contribution of this surface component, and here these grains are smaller than in the case of for the sample with small amount of surface magnetite component. In fact, here you can see some conglomerates, big conglomerates of grains. This scale is 50 micrometers, but we expected that the magnetic cores of magnetite is of order, for example, 100 nanometers. So we cannot see them, but somehow the total size of grains is connected is proportional to the size of magnetic core in these samples. In this plot, we collected the values of so-called stoichiometry parameter of the magnetite. It is the ratio of the contribution of iron atoms in B position, this octahedral position, to iron in tetrahedral position. Theoretical value for entirely stoichiometric magnetite is 2, and only these 2 natural samples have these values close to 2. But for example, this sample from Czech Republic has really very small value, even less than 1. It means that it is another proof that this magnetite from this place is very defected, non-stoichiometric and oxidized too. You can also see the values, the contribution of the hematite in relation to all magnetic or ferrimagnetic phases, and the domination of hematite is visible in the case of this Norwegian sample, Mo i Rana, probably because in this iron ore dressing plant there was a lot of hematite, and it has been transmitted via winds to the forest, to the fields, and it is this influence is very clearly visible here. In this plot, you see the values of hyperfine magnetic fields, which are the parameters of Mössbauer spectra, the values both for this A and B position in magnetite, and we can say that there is some kind of correlation, linear correlation between these values, not perfect, but it is. So one can conclude that if we have some influence, some defects inside the magnetite, they changes whole electronic structure of magnetite. And very, I think, trivial observation that if we have samples of natural magnetite, very stoichiometric, can see that the values of both hyperfine magnetic fields are the highest. Okay, I don't like to read very detailed conclusion from this part, but I would like to say that we can believe that mineralogy, I mean the contribution of each phase and also detailed hyperfine parameters of the Mössbauer spectra are the good characteristics for these topsoils, for the technogenic magnetic particles inside these soils, and this results from Mössbauer spectrometry could identify the sources of technogenic magnetic particles emission. Another group of samples are the fly ashes. First, from the heat plant, even 2 heat plants, which are located just in my town. They use so-called chain grate stoker, and in other places spreader stoker to burn the coal. And the temperature of burning zone is about 1100 Celsius. These fly ashes are trapped by natural gravitational system multicyclone mechanical collector. For the investigations, the ash has been divided into granulometric fractions, coarse and fine. And what we can see in the Mössbauer spectra. Okay, as usual, hematite, magnetite, a bit ferromagnetic goethite. Also, quite huge contribution from aluminosilicates, but not the same like in the soils. We can see that the lines are more wide, are broad. Why? Because of high temperature, because of vitrification processes. These phases are glassy phases. Maybe even spinel is present here. But the most interesting feature is the presence of the components, not too much, but still visible. The component which could be associated with a metallic iron, or maybe iron carbides too. But from where we can find the metallic iron in fly ashes? The answer could be quite simple. Possibly in fly ash we can have unburned coal, and coal has, of course, a reductive potential. So we can expect a kind of metallurgical process, a reduction of some part of iron oxides, and that's why we can see, of course, very small particles of metallic iron here. And what about fly ash from power plants? In fact, this power plant is also located not far from my town. It is the biggest power plant using just hard coal. And here there is a very special pulverized coal burner with high temperature burning zone, about 1800 Celsius. And fly ash is trapped by electrostatic precipitator with several sections. And the spectra are quite similar, but this part of the paramagnetic part of this spectra connected with aluminosilicates is even more glassy, more white. And we also can see more metallic iron here. So two different systems, two different situations, but the same thing, that during the burning the coal, we can expect some traces of metallic iron. And it is, I think, the main conclusion from this part, but we can also see some other details. For example, the detailed mineralogy of these ashes depends not only on the burning temperature, but also on the granulometric fraction. But there is some general tendency that the higher combustion temperature is the higher content of magnetic ions we can expect. And the third part of the samples are the dusts from ventilation and air conditioning systems. They were collected from vehicle diagnostic laboratory halls, which are located in our university in the Faculty of Transport and Electrical Engineering. You can see the general view of the several sections of such a filter, and you can see, of course, a lot of dust. We have made just a standard room temperature transmission Mössbauer spectrometry. In fact, for each section, we repeat many times. I present just the first spectrum because they were very, very similar to each other. And we can see a domination of such central structure in the spectra. Probably it came from the soils, which can be incorporated inside the building just as an effect of the ventilation system and the wind, of course. But probably this very, very huge contribution is also connected with some very small particles of goethites, superparamagnetic particles. But the most interesting question for me was, can I see a metallic iron here? Because the metallic iron is a sign of a fresh anthropogenic activity. And yes, we can say that there is something. There is some component of 33 Tesla, is a value of typical characteristic hyperfine field for metallic iron, and there is something. It is this component of about 7% abundance, but it is very wide. So we cannot say definitely. Mössbauer spectrometry is inconclusive in this question, but it gives some arguments for the presence of the metallic iron, but it demanded some further investigation. We decided to make just magnetic measurements, magnetic hysteresis curves, using squid quantum design. It was made by our colleagues in Warsaw University. And we also prepared special software. I named it HistFit, because many people just plot hysteresis loop and sometimes determine the coercivity, for example. But in many cases, such a hysteresis loop could be a superposition of several hysteresis. That's why we made it for such decomposition. This software is based on the Excel and the solver add-in, which is present inside Excel, and also we had to write some code in Visual Basic, but very simple one. And this software is good not only for fitting, but also for simulations, theoretical simulations of hysteresis loops for the mixtures of different constituents. For example, if we have 90% of magnetite, which can be thought as a high coercivity constituent, and if we have just 10% of metallic iron, which is very soft in the magnetical sense, of course, we can expect very characteristic wasp waste profile here of this hysteresis loop. We made the measurements for our dusts first at very low temperature in 2K. And when we applied our software, we could see that, okay, after extracting the superparamagnetic contribution, here we can see that the experimental hysteresis loop could be a superposition of two hystereses with different values of coercivity. But at the room temperature, it is not the case. One hysteresis loop is enough, and the value of hysteresis of the coercivity is very typical for just magnetite at room temperature. So still we have inconclusive method, or we cannot understand something, and we must think for a moment why we can't see the traces of metallic iron looking at room temperature hysteresis loops. Probably the problem is in the size of the grains. As I mentioned, we rather expect very small particles of metallic iron. So maybe they are just superparamagnetic from the macroscopic point of view. In the Mössbauer, they are still visible because Mössbauer is very fast, 10 nanosecond probe. It is a characteristic Larmor precession time. Yes, but in the case of just static magnetism, there is nothing at room temperature. And another reason could be the plenty of defects in such small metallic iron of technogenical origin inside the dusts, and such defects could enlarge magnetocrystalline anisotropy and elevate the value of the coercivity. That's why the coercivity of usually soft iron could be very similar to the coercivity of dominating magnetite. And we have found the confirmation of such suspicions. I was looking through our old papers made not by me but our team in our Mössbauer laboratory in cooperation with some other groups in Korea, for example, and in Warsaw. And here you can see intentionally prepared iron nanowires and iron nanoparticles of the size less than 100 nanometers. And in the Mössbauer spectra, you can see, okay, metallic crystalline iron, but also we call it amorphous iron, very broad structures. The same in the next paper, also from our laboratory, and we also see very broad structures. And here you can have directly plotted distribution of hyperfine magnetic field, very broad. So and this result is confirmed both in the case of transmission Mössbauer spectrometry and conversion electron Mössbauer spectrometry. The spectra are very wide, but it is still only iron, nothing else. And when we look at the hysteresis loops, you can see something strange. Okay, no wasted feature because it is not a mixture. But if you see, if you look at the coercivity, this coercivity is not 10 times smaller than magnetite. It's 3 times higher. It means that so defected and so small particles of metallic iron have so hard magnetic properties, and very similar to the magnetite. And I have found also another work, not our work, which was devoted to artificially made nanoparticles of iron, and they also can see this very broad distribution of hyperfine magnetic field. That's why probably we see something similar in our environmental samples. And this is a reason why these components attributed to iron, metallic iron, is so wide and difficult for interpretation. Because here you have only iron, so it is obvious. But in our cases, the iron, these components, maybe 10% of whole spectrum and whole. Okay. Now I would like to present you maybe the last paper. It is the only one found by me in the literature when you can see very beautiful contribution of metallic iron, very sharp one, and it is in the case of airborne atmospheric particulate matter. It is something unusual because maybe it is the only Mössbauer work on such a dust, because it is very difficult to collect enough matter from the air to make a Mössbauer spectrometry. They applied a very unusual system to do this. But why they have so many metallic iron here? Probably the place of collection was very close to the railway junction in Munich, in Germany, and probably they have continuous source of metallic iron, of course, because of some kind of friction when the trains was traveling through the rails. And of course, in this case, they could see this special wasp wasted feature in magnetic hysteresis loops, so they are happy. And also they see the shift of Curie temperature towards higher temperatures. So they really could see beautiful iron, but it is an exception, something unusual. Normally we can expect no iron or very defected iron, as I showed. And the last trial to verify if we really have this metallic iron in our indoor dusts from ventilation system. Simply, I decided to make an experiment using synchrotron radiation in Solaris National Synchrotron Radiation Center in Poland, in Krakow, located in the university campus of Jagiellonian University in Krakow. Many thanks, special thanks to Dr. Marcin Zając for the sample preparation and for giving me a nice opportunity for remote control of such huge experiment from my home in this difficult pandemic period. Here you can see some details concerning the mounting of the samples on the carbon tape of indium foil, and also some ideas concerning a very special method of detection, this total electron yield mode, very effective, very sensitive. Okay, and what are the results? Here in blue you can see experimental curves. They are not the curves of absorption. Okay, the method is of course based on absorption, but the detection is based on the measurements on the current of emitted electrons, so it looks like emission. And this method, of course, is sensitive to the fine structure, not only to the presence of given element, but also to the fine structure, to the environment, chemical environment. So in this spectra, we can see dominating structure of the hematite, but as you can see on the reference spectrum, the absorption should start above 705 electron volts. Our experimental curve starts earlier. And here you can see the spectrum for the crude sample and here for the magnetic separate. And even here you can see that this part of the spectra is similar to the reference spectrum of metallic iron. So probably it's a next argument for the presence of the metallic iron in this dust, but the statistics should be better, and probably this iron, I'm even sure that it is really really defected. That's why it's not easy to detect using any method. And I can formulate the general conclusions that the mineralogy of soils, and for example, non-stoichiometry of magnetite, the contribution of surface component magnetite in the spectra, it could be a good characteristic, good identifier for technogenical magnetic particles, and could be used for monitoring the influence of industrial emitters on the environment, on the forests, on the fields. The mineralogy of fly ashes is also very interesting. We can see some traces of metallic iron there because of reductive potential of unburned carbon. Also, we can say that in the case of indoor dusts, some presence of metallic iron, which is not so obvious, but I believe that I proved that it is. So this presence could be a sign of fresh activity, of human activity, technological activity, and also it would be helpful to identify the real sources of these dusts which are around us inside the buildings. And also we have prepared, I would like just kindly remind that we prepared this simple software for the hysteresis loops decomposition, and you are kindly welcome to cooperate if you have some magnetic hysteresis loops. We can try to process them and to formulate some conclusions concerning environmental samples, which are very, very complicated mixtures of many compounds, many minerals, and some anthropogenic constituents. My special acknowledgements to Professor Jacek Szczytko and Mr. Marcin Witkowski, a PhD student in Faculty of Physics in Warsaw University, for very nice measurements on the squid, magnetic measurements. My thanks to Professor Waldemar Tuszyński, Tanita Mańkowska-Snopczyńska for the optical micrographs of topsoils, magnetic separates of topsoils. This group is located in Radom, in the Institute of Sustainable Technologies, and my work is usually founded in part by the Polish National Science Center. Thank you for your patience, for your kind attention, and I hope that in the near future we can meet in normal way, face to face, without pandemic. Many thanks, merci, shukran, dziękuję.
Thanks, Professor SZUMIATA, for your excellent presentation about Mössbauer spectroscopy. And now it's time for questions and comments.
Yes, please, yeah, welcome, with pleasure.
And maybe we can start with Professor Ahmed Nawi, because he already made some comments and the questions in private as a private message. Professor?
Yes, thank you very much. Can you hear me here? Because I'm using
I'm here. Well,
I'm using my iPhone, that's why it's a little bit difficult. So I think there are a lot of very good work, what it can be in collaboration with Morocco regarding Mössbauer. If you take olivine, which is the core element or material for lithium-ion battery based on iron. And I read some, since I know that today you have this talk about Mössbauer, I read a little bit about Mössbauer, and there are a lot of work done using Mössbauer and during the preparation of olivine, which is, that's the discovery from the biggest discovery for the lithium-ion battery from Professor Goodenough, who got his Nobel Prize just last year, I guess. And by annealing the olivine, there are some iron 2O3. I think this is hematite, I guess, which is as a byproduct. And therefore, in this area, I think it will be a very interesting to have a cooperation with the group working on batteries in Morocco. And that is just a comment. My questions now: what is the resolution of Mössbauer spectroscopy to explore the valence state of iron and iron phases, in your opinion?
It's a very good, very general question, but not easy to answer. Of course, I can say that Mössbauer spectrometry is probably the best method for distinguishing the iron compounds, but sometimes it is not very easy. I play usually with magnetic systems, and in this case, the nuclear states are split magnetically, and the value of characteristic hyperfine magnetic field is a good identifier for the phases. Sometimes, of course, this value it tells maybe not directly about the valence state, rather about magnetic ordering, but still it's a good identifier. If you have a paramagnetic material, you can see only the isomer shift and also quadrupole splitting. So you have only the central part of such a spectra like I have presented here. And it is, of course, necessary in that case to change the energy scale to make the measurements in the narrower scale of velocities, because we use a special scale of velocity. And in this case, very thorough analysis of spectra usually allow to distinguish many paramagnetic contribution of different valence states. There are some standard, I can say, some standard papers where you can find the values for isomer shift and quadrupole splitting, and you can compare in your work. But I play usually with environmental samples, which are so complicated because they have so many different phases that sometimes I have a huge problem to identify. But for more pure, intentionally prepared materials, probably Mössbauer would be good enough for the purpose of identification. But if you would like numbers, just some valence scale, I don't know at the moment definite numbers of precision. I can find it in the literature for you. And many thanks for this comments concerning the cooperation. I am, of course, very open to this. I have also colleagues in other places which also could be involved in some project, maybe with some other country from European Union. We can really think about serious project about the batteries and the role of the iron here, because up to now I thought that iron is not important in the context of new batteries, but I was wrong. Okay.
Since you say this, I want to add the following. It's not only for batteries, the iron is very important, it's also for solar cell. And I did some work long ago, starting with iron oxide. And by sulfurization of iron oxide, you can, if you look to the Gibbs diagram, you can understand that thermodynamically, you can convert iron oxide into iron sulfide by sulfurization. And the iron sulfide, what we call pyrite, I work very much on it, which has a band gap close to 1 electron volt. And it's very good candidate for solar cell, but there are a lot of defects in this material. But it's very interesting to investigate this kind of materials. But thank you very much.
Our spectrometry, it's possible to see the defects.
Yeah, thank you.
Okay, thank you.
Thank you very much.
Thank you.
Thank you.
I'm ready.
Okay. Okay. Is there another question, please?
Yeah, could I?
Yes, yes, Professor Sier.
Okay, thank you so much for your nice talk. Just I'm wondering, for example, if for the well-defined nanoparticles, for example, what your software could do. For example, when we have already well-defined nanoparticles that we know the sizes, and sometimes we do the regular magnetic characterization, and we see, for example, the hysteresis. From your software, what we could extract, like additional information that we couldn't get with the regular, when known in the classical way.
I think it seems to me that this software is predominantly good for the mixture of phases, and not very magnetic. I mean, it is good for environmental samples, because this, for example, two magnetic phases shouldn't be strongly coupled with each other, and it is the case for the environmental sample where you have the domination of paramagnetism or no magnetism, some sand for it, no magnetic sand. In the case of, let's imagine, nanoparticle of magnetite, for example, okay, maybe iron nanoparticle with magnetite at the surface. Yes, so yes. I think it is not good enough, this software, because these two phases are very strongly coupled, magnetically coupled, not separated, not accidentally mixtured. So I am not sure if my software would be enough, because it is good when we have just a superposition of two separate phases.
Yeah, I got it.
But of course, we can introduce some kind of interaction. It is not a problem, but it's just my first step. It was written 1 month ago, and it works for the environmental samples. But we try to work more on it. Okay.
Yeah, sorry, I saw that you have some data around 2 Kelvin Did you, for example, real measurement or the prediction from simulation?
No, it was a real measurement, but not on the beautiful nanoparticles, but on the dust. Because these real measurements made by me recently, okay, not by me, but my colleagues in Warsaw University, it was these samples of dust, where you have plenty of non-magnetic stuff. But after that, I was showing some literature data concerning intentionally made nanoparticles, and for them I didn't try my software because I didn't have no access to the original data, so I don't know how it works. For materials, I was playing with environmental samples only.
Okay, thank you so much. Thanks.
Okay.
Thank you. Professor TADEUSZ, you can ask your question.
Thanks a lot, Professor TADEUSZ, for this nice lecture. It was a pleasure to meet you in Ikamana last year. We are happy to meet you. Yeah. I have two small questions. What about the other instrument like ICP or microscope, or to compare with your Mössbauer materials? The second one, did you have any idea about we can detect some low spin, high spin, especially talking about iron? Thanks.
Thank you. Okay, it was my dream to show you the pictures from scanning electron microscope. But in our town, not in our university, but in the second institute, they have too good equipment. I mean, they use magnetic lenses in this microscope, new generation of microscope, and they don't want to put inside my magnetic powder because it was not a problem for the synchrotron. Okay, there they have also a vacuum chamber, but no magnetic stuff at all, no electromagnets and so on. That's why, okay, I will be trying to find the place with worse microscope, but which would be more suitable for this case. ICMES, it will be possible to make it in Radom, in the Institute of Sustainable Technology, but simply I had no time to do this. Of course, ICMES provides the information about the elemental content, not hyperfine structure, but of course it is the basis. Simply, even I should have started with this, but I didn't do this. Sorry. Of course, before any publication, it is necessary to make elemental analysis with this method. They also have XRF, but very enhanced method with wave length detection. So it is better than standard XRF, so maybe it will be also suitable for this case. And your question about crossover, spin crossover, high spin, low spin, okay, it is good, okay, it's very interesting subject, but rather when we are thinking about some metal organic compounds, and I had some connections with this such subjects with Professor Jan Garcia, for example. But of course, with pleasure, I can try to play with other groups and with other compounds. The only problem is that in this case you need to make a temperature scan, and the Mössbauer is rather long time measurement. So we can make, for example, in the liquid nitrogen, the temperature measurements at the room temperature, or higher, but just several points, not 100 points, because it would take about 1 year or 2 years such measurements. But still, it is interesting if we can do such several measurements. So if you have some ideas, I would be very, very happy. And once again, thank you for last year meeting. It was marvelous. You are my friend, and I am your friend.
Thanks a lot. Thanks a lot.
Thanks a lot. Is there another question? No?
I have one if there is no one.
Yes, Professor Ahmed. No.
Yeah, I just want to go back to this high spin and low spin configuration. And I think for catalysis and photocatalysis, if you just consider a mixture of iron and other transition metal chalcogenide during the sulfurization in sulfur compound. If you have a low spin configuration, mean you have a band gap, because the low spin configuration, this means all electron will be in the TADEUSZ banding and the OUARGHI will be empty. And this means you have a band gap, and this can be interesting to prepare some photoactive materials. And therefore, I think maybe if you combine Mössbauer spectroscopy to see the valence of the iron in the mixture of iron and other transition metal chalcogenide in sulfur compound, and some spectroscopy where you involve the light, it will be interesting for to prepare some new material for catalysis and splitting of water.
Yes, from the iron point of view, the Mössbauer would be, of course, unreplaceable technique. But if you need maybe to look at some other transition methods, maybe this synchrotron absorption methods would be also good. XAS, for example. I can think about this.
Yeah. Yes. I'm just talking about a mixture between iron and the other transition metal chalcogenide, because if the ratio of iron into other transition metal chalcogenide like ruthenium, for example, have a very big impact on catalysis. And I think if you add to iron another metal, you will see it in Mössbauer spectroscopy, I guess. I hope you. Okay. Thank you very much. Thank you very much.
Thank you. Okay. If there are no more questions, we can close the session. Professeur Hamouti, c'est Hamouti. Donc, je pense qu'il n'y a plus d'autres questions, donc on peut clore. Professor Hamouti?
Yes, I am here. I activate my microphone. Thank you so much, Professor TADEUSZ, for your participation. Thank you for this very interesting lecture. Thank you, Professor HOSSAIN Al-Warghi from Al-Husayma. Thank you for your participation, and hope to see you in next conferences of this ICMES 2020.
Yes. Thank you, Professor SZUMIATA, for this amazing conference and fluent explanation, and see you next, inshallah.
Yes. Masa al-Khair.
Masa al-Khair.
Goodbye. Thank you.
Goodbye.
Goodbye.
Thank you.
Goodbye.
Thank you.
Shukran. Thank you.
Shukran. Hello. البروفيسور مزيان